Great. Sounds like right now we have more time to talk about the research results. We really appreciate. I know that everybody is looking forward for the research results. So if you could please maybe, yes, it will be the first one. Well, number one, yes. So again, for the NMSU team, and actually we have a very large team, and you will see some of our researchers, faculty members, and the students here, but we also have a lot of students working on this project. I really want to appreciate all their effort and the contributions. So today you will see a lot of details of the research results. And even though we say right now, because it's preliminary data, it's not for distribution yet, but we fully understand that we need these details in order to support the statement that if this water is safe. And so far you will see all the results that how we have treated this water to a safe level, and related to the targeted analysis results and some non-targeted analysis and the toxicity study. But we will work with Zach and to make sure that when we have this public outreach and education activities, we will include enough details to support the statement. So with that being said, we will start our first presentation is from Dr. Punshasa about targeted analysis.
Okay. Good morning, everyone. Thank you, Dr. Xu. I'm Punshasa Senanayake. Today I'll be I'll be discussing about target analysis of treated produced water via membrane-based and thermal-based system. As you can see, it's a group work. I'm presenting behalf of everyone here. So this work is scientific based. We use scientific methods to analyze this to see whether the treated produced water can be used in fit for purposes applications such as agriculture, surface discharge, surface water discharge, or cooling tower. Likewise, whether we can convert this or recycle this produced water for fit for purposes application. And our goal is to give some clarity for entities to in decision-making process in New Mexico State and beyond. With that saying, today I'll be covering these topics under my presentation. Sorry. First, I'll be briefly discussed with you about a treatment train, or the major component of that, what will be covered under target analysis, the thermal and membrane-based systems that we evaluated, and these targeted analytes are divided into tier 1 and tier 2 components. We will go inside this tier 1 and tier 2 and see what are the removal percentages and whether we see any anomalies. And we'll discuss about the effluent water qualities, the variabilities we see in this effluent water quality, and I'll anchor the presentation with summary conclusion and next steps. So if we take a rough treatment train, what happens is we take the raw produced water, it goes through a pre-treatment system. It can be biological, it can be chemical, it can be physical, it can be a combination of these treatments, and feed into primary system. It can be membrane-based and thermal-based, which my presentation is mainly focused on. So I'll be discussing about the feed and the effluent water qualities of these primary treatment systems. When we come to target analysis, we use NPDE plus list, which is over 700 components, and the systems we are discussing today here contain 6 thermal systems and 4 membrane systems. So thermal system starts with letter T to indicate it's a thermal system, and the membrane systems start with M, and ABC nomenclature goes based on the site, and 1, 2, 3 is for represent whether we have done sampling 1 time, 2 times, or 3 times. In thermal systems, we have in-house system and a collaboration with Colorado Schools of Mines. So, as I mentioned, NPD plus list is over 700 components, and out of the over 700 of these components, 609 components of these analytes were at least sampled once, and 290 was detected at least once in these samples. So it can be raw or distillate or feed streams or RO permeate, regardless whether which stream it is. We have only detected 290 components over 700. And these components are divided into 16 different categories, which comes out as metal and metalloids, and anions and organic compounds like SVOC, VOCs, which I'll be discussing in later slides. So if we slice this data in a different manner, as you can see, I have categorized them according to the 16 different families. You can see some of the families are not there in either raw produce feed water or the effluent waters. We have 7 raw earth elements and 6 PCBs, which we measured 6 times and 11 times respectively, but we didn't detected them at least once. With that, let's move on to the tier 1 category. So tier 1 category basically means which you can get data pretty easily by measuring conductivity, pH, doing evaporation studies, likewise pretty hands-on on-site reading. So we have 21 tier 1 categories, but I have summarized few of them just to illustrate that the variation that you see in these feed waters. For example, if you look at TDS, total dissolved solid, membrane-based feed varies from 75 grams per liter to 175 grams per liter. And the membrane is not second for the thermal system, where the variation goes around 100 grams per liter to 175 grams per liter. So it's a huge variation. So just to give a prospect on this, the brackish water is 3 grams per liter. Brackish water concentrate or brine is about 12 to 17 grams per liter, and seawater is about 35 to 40 grams per liter. So you can basically pitch all these inside the variation that you see here in the produced water. So as you can see, it's pretty challenging, it's pretty dynamic. But the good thing is, if you look at the effluent, which is end with either ME or TE, you'll see the variation is really small and the concentrations are close to 0. For example, TDS, it's around 3 to 5 grams per liter, regardless whether it's membrane or thermal-based systems. The huge variation or the least removal percentage is observed in alkalinity, where the membrane base was around 85% and thermal base was about 89, close to 90%. Other than that, rest of the systems, rest of the tier 1 categories, removal efficiency is close to 90%. Regardless of the high challenging water, you can see these technologies have done great work removing most of the compounds as whole. So let's move on to the tier 2 family, which will be digging into individual components. For your reference, I have color-coded the bars. You can see that if it's dark green color, that means the feed and effluent is above detection limit. And if it's light green color, it's a membrane-based system where both feed and effluent is above detection limit. So there are incidents where we see the feed is in the detection limit, but the effluent is below detection limit. So in such case, I have color-coded them in orange and yellow and orange for thermal and membrane-based system respectively. And for the calculation, I took the detection limit as its concentration, because the concentration can be either detection limit or zero. So it can be vary between the detection limit and zero, but this is the maximum. The worst case scenario is plotted here. So as you can see, regardless whether it's a membrane or thermal system, the removal as whole is 97%. So even the boron removal is around 90% for both membrane and thermal system. The effluent concentration still contains significant portion. In general, both vary around 2 to 5 milligrams per liter. So we will discuss this in later slides, how this influence when it is used in fit for purposes application. The significant difference between the membrane and the thermal system comes from the silica, sodium and chromium 6, where you can see thermal systems push this concentration, these compounds to below detection limits, while membrane-based system we observe some of these compounds above detection limits. When we move on to anions, there's no significant difference between the membrane and thermal systems, where both remove over 90%. Carbonate, borates, and chlorides are the common effluent anions we see above detection limit. Sulfates and the rest of the halides are below detection limit. Radionuclides, which is one of the challenging areas, and more focused area, where you can see, regardless whether it's a thermal or membrane-based system, you can see a removal over 98% and push the concentration below detection limit. There's a marginal error in membrane-based system when we compare the Gauss alpha and Gauss beta, but it's just a marginal advantage below 2% difference. From inorganics, let's move on to organics. Let me start with oil and grease. For thermal system, we did not see any oil and grease in the feed stream, therefore we don't see it in the effluent stream. But for membrane system, we see there are 3 studies report feed streams contain oil and grease, and 4 for effluent. This can be due to adding lubricants or something related to that end, but as you can see, it removes around 97% of these compounds. The next family of compounds of organics that I'll be discussing here is the volatile organic compounds. The family is pretty huge, and the removal efficiencies vary somewhere around 18% to 99+%. And there are incidents where we see negative concentration. This is due to accumulation of these compounds in the effluent stream. So this actually doesn't mean it's really bad. So I'm discussing this value here. So as you can see, it's negative 1000+%, but it actually doesn't mean it's really bad, because if you look into the maximum concentration we observe is 1 milligram per liter. So it's a numerical factor that comes into play to show it's a huge negative impact. But if you debug the situation, you can see it's pretty lower number. So as I mentioned, it varies from 18 grams per 18.5 for thermal system to 99+%. But some of the key factors I need to highlight here, the ones that are highlighted in light red color, these compounds can be seen in the effluent water qualities as well. That means even after post-treatment. So we need toxicology analysis and further analysis on this, which will be discussed in later today. But in Uh-huh.
Because I'm not understanding. 1 milligram per liter of butanon is really, really bad.
Yes, yes.
So if you're detecting then in the concentrate or in the distillate?
Distillate, low. So it's for RO, so RO permeate.
So you're going to get milligram per liter of it in the
Yeah.
quality. So the RO is concentrating.
Yes,
That
yes, yes, exactly. So negative numbers mean the system concentrate that compound in the distillate or the permeate stream.
Yeah.
So during the thermal distillation process or the reverse osmosis process, certain chemicals could preferentially transport to another phase. Just for example, some volatile organic compounds, they can be concentrated. We call it, it's not in the brine or in the concentration because they prefer the transport to another phase. So you see higher numbers in the product water. But these results Punshasa are showing are from the desalination process. And then later, you also have the post-treatment. It's also be good to look at the post-treatment. One example, this is an example. Another example is methanol. You know, methanol is so volatile, and then you see higher concentration in the distillate. So basically, later, this emphasized the importance of the post-treatment of polishing.
From a regulatory standpoint, those are the kinds of things that we want to look at as indicators or red flags for permitting.
Yes. Yeah. Thank you, Jason.
Thank you. Yeah. So for clarity, that means these negative value means they are concentrated in the distillate or the RO permeate stream. But regardless of that, we observe 21 different VOCs in thermal distillate and 23 VOCs in RO permeate streams. When we move on to SVOCs for thermal systems, as you can see, some of them are concentrated, and I think methanol is right here. Right here. So, as Dr. Shu was highlighting, some of these compounds prefer moving on to the distillate via through these systems. So we see 25 different SVOCs in the distillate prior to post-treatment. When we compare the SVOCs for thermal versus membrane system does a better job where we only see 5 VOCs here, but similar story plays around here where some of these compounds concentrated after in the RO permeates. There are other organic compounds where we see in the system where we analyzed. Here the membranes membrane-based systems do a pretty good job on removing them. There are fluorosulfones and total organic halides where we see in the membrane-based system effluent above the detection limit and lower removal percentages. So this is the fact that Dr. Shu was planning to highlight, that we compare the current thermal system effluent versus drinking water quality, and we evaluate the system after post-treatment of these thermal systems. As you can see, ammonia and boron, for example, are pretty high, recorded if you look into the maximum number. But after post-treatment, we see these concentration decrease some to below detection limits. For membrane-based system, the story is same, where if you take benzene, which is highly carcinogenic, we see the maximum reported value is about 16 milligrams per liter, but after post-treatment, these values go below detection limits. So the point that I was trying to highlight is just the primary treatment system by itself is not sufficient. Proper organized post-treatment is necessary to remove some of these compounds from the system when we want to push this treated produced water for fit for purposes application. So a robust pre-treatment should be there to generate the specific water quality for the primary treatment system, and a organized post-treatment system should be there, which is customized for the system to remove some of these compounds for the fit for purposes application. The reason I was highlighting that we need a robust pre-treatment system is due to the variation we see in some of the effluent water qualities. So there was one study where we did sampling 5 times, and we see a significant variation. So as you can see, the standard deviation is almost as value as average. So the variation is significantly high. So this can be due to this variation that we observe in the raw produced water. So if we have a robust pre-treatment system, we can make the primary treatment system feed at a static values for these compounds, which improves the removal percentage as well as the lifetime of these treatment systems. With that, the conclusion and the summary of my study that I presented here is that we looked into 6 thermal systems and 4 membrane systems, study over 600 plus components, and we looked into feed and the post-treatment, feed, effluent and the post-treatment of these systems. In general, the removal percentage of majority of these compounds are over 95%, and thermal systems have membrane systems show a better removal of the organic compounds, some of the organic compounds over thermal system. But regardless whether it's a thermal system or a membrane-based system, post-treatment is a key component when we push this produced water for fit for purposes applications. For next studies of next steps of this study, we will be further analyzing these results and try to accumulate more treatment train evaluation into this study, which give us a broader knowledge about the technologies. And second part of the study, we will be looking into the physiochemical properties of these compounds and try to connect it with the mechanical properties of the removal system. For example, melting point, boiling point, molecular weight might play a critical role in removal percentages. So we'll be looking into that study as well. And we are trying to introduce a surrogate model. That means whether we are trying to see whether we can monitor a TDS or conductivity or pH or a combination of these variables and see whether there's a correlation with the compound concentrations. So by that way, we don't need to go through a rigorous process of this monitoring, especially when we push these technologies into full and pilot scales. Toxicology analysis is pretty important, and Dr. Chang and her group will discuss about this in today's later presentation. And risk assessment is also a key component. We have initiated this study, and hopefully we can present that in a future event. And we are preparing 2 manuscripts at the moment for the thermal and membrane-based system separately. So currently we are working on the 0.2 and 0.4, where we try to see a correlation, where we try to develop the surrogate model and try to see whether there are physiochemical properties and mechanical removal stability between these technologies. With that, I would like to end my presentation. Thank you everyone for listening, and if you have any questions, I'll be happy to answer them.